look at the size of the residuals, and look at your interpretation. So the idea of interpretability is this idea that you should have at least 3 items loading on each factor, right? So remember, your factor is your latent construct, which means you should have at least three variables that are heavily loaded on that you have actually observed. So ideally, your variables should have some sort of conceptual meaning if they're grouped together somehow. Variables between the factors should be measuring different constructs, different constructs. Yeah. And we're going to try and use a rotation to maximize interpretation, maximize the ease of interpretation. So the Kaiser-Gutmann rule is something that I've already talked about. Right? It's this idea that the eigenvalues are bigger than 1. Right? So how does that work? Just to repeat myself. Right? We're saying just choose those factors, if we're using the Kaiser-Gutmann rule, just choose those factors or those eigenvectors that have an eigenvalue bigger than 1. Because if you have an eigenvalue less than 1, basically your PCA vector or your factor is explaining less variation in the data than one of the original variables. So obviously that's going to be, this is true with respect to your PCAs, but with a factor analysis, we're inserting our communality estimates, right? So in fact, the variance is going to be less than P. So in fact, we should probably, instead of looking for an eigenvalue less than 1, you should be looking for an eigenvalue less than the average eigenvalue. Okay, and prop factor has a few options to let you look at this. It'll be in the lab. Okay, we can look at percentage variance, but we've already talked about this. I said before, some people like to use the 70% or 80% cutoff value as to how many variables, how many eigenvectors I should include. It is completely arbitrary, so I'm not a big fan of that. But I think actually this is the default for some reason in SAS. It just chooses the number, it analyzes the number of factors until you're explaining about 80% of the variation. So scree tests we've already talked about, right? This is just in your notes. So you're just plotting your components and your corresponding I values, and you're looking for an elbow in the plot, right? What am I saying here, right? Your eigenvalues are of R and a PCA. A rule of thumb is that. Oh, okay. So, right. In a factor analysis, right, your scree plot can look a little bit funky because you can have negative eigenvalues. Why can you have negative eigenvalues? Because you have these, you've made this tweak to the diagonal so that you've got a correlation matrix that's not really a correlation matrix anymore, and that variables are not perfectly correlated with one another according to your correlation matrix, right? So you can get negative eigenvalues. It still can be useful, but it takes some getting used to. Okay, that's not really important. So this is just sort of a list of contrasting a PCA versus a factor analysis, right? Because it's easy to conflate the two, and a lot of professional statisticians do, right? In a PCA, you don't discriminate between communal variation and unique variation, right? You're just saying there's just variation. That's all it is. Just these are the variables. That's all there is, right? A factor analysis is different, right? We are only interested in trying to analyze the communal variation because that's the stuff that we think is created by the latent constructs that are underlying this, right? The variables in a factor analysis are reflecting the latent constructs, right? In a PCA, we don't look at that. All the components are derived solely from the variables, and they explain 100% of the variation in the data. So we just take the variability as it is, right? Factor analysis, as I've stated, we are splitting into 2 parts, right? And that basically goes further down here. Obviously, for a PCA, we know the components that we get are theoretically just linear functions of the variables, and the variables are just linear functions of the components. For a factor analysis, the variables are theoretically linear functions of the factors, these underlying constructs only, right? in a factor analysis, the loadings and scores depend on the number of extracted factors that you get. So you might go with the data, if you run one of the data sets that we're going to do in the lab, right, and try and say, okay, look, I think there are 5 factors here, do the analysis. Now let's do it with, extract 3 factors. You'll find that the loadings will change. They wouldn't change in a PCA, right? The PCA doesn't look at that at all. It just says, here are the loadings of PC1, here are the loadings of PC2, PC3. It doesn't matter how many PCs I'm choosing. Right? So often with the factor analysis, it does matter. So if the factors are doing a good job in explaining the correlations, right, you expect the predicted correlation matrix, R star, to approximate the input correlation matrix. Right? So we would expect the residual matrix, which is the difference between these two, to be close to 0. And we can use this in the proc factor statement and examine that. But we'll do that in the lab, I think. The maximum likelihood method is something you will also do in the lab, right? So this is the different way of analyzing your, or trying to find your factors. It gives a chi-square test for significance of the residuals that we talked about. So this is the idea that we can use these residuals to determine whether or not we have got enough factors, in our model. And this is what we can analyze. The first test that we're going to get, the null hypothesis, that's H naught, is that no common factors can sufficiently explain the correlations that we've observed, right? This is the one that you want to reject, right? This is the one that say, hey, look, if there are no common factors, if there's no latent structure in the data, then I got nothing, right? There are no correlations here. There's no vector that goes through that's particularly useful to me that explains the shared correlations going on. Right? So hopefully you have some structure in your data so that at least one of the variables is one of the vectors is describing a latent construct. Right? So if you get a non-significant value for that, that's a problem. Right? Basically it's saying there's no structure, you don't have correlations between your variables that are strong enough to warrant actually saying there is some sort of underlying thing that's creating correlations between them, because you couldn't see them. Now here's the problem. The second test you would think would be really nice because it would be a way of describing how many factors I could use. It's the null hypothesis is that the number of common factors that you've chosen, let's say you chose 5, right? That's sufficient to explain the correlations that we saw amongst the variables. So n is the number of factors that you have specified within SAS. Right? You'd think that would be really useful. You would say, hey, look, okay, let's do this test. I look at my null matrix, my residual matrix. Is that small enough to say, well, I've got sufficient numbers? That's in theory what I could do. Right? So this would be useful for testing the hypothesis that the chosen number of factors that you've got is actually sufficiently describing your data. Right? Here you would want to reject your null hypothesis, right? You want to get a large p-value. The problem is that this test is really sensitive, right? The maximum likelihood method works well with a lot of data. Right? You need a lot of data to actually estimate all these parameters well under a maximum likelihood estimation. But if you've got a lot of data, this particular significance test is overpowered and it will pretty much always reject it. So it's not a very good test, not a very useful test. You'll find this out anyway. So that doesn't really help us. So I state here, the downside of this test is that the chi-square test is sensitive to sample size. So the test normally rejects the null even when the factor analysis solution is really good. Okay, so this is the lab. Basically, the lab that is now available on stream. I'm sorry I haven't printed it out because this was supposed to be done in block 2. Is available for you. So it is math attitude data. So there are 12 questions that I think were asked of students about the utility of maths in their life and in their career, right? And there were a lot of student responses. So there were almost 2,000 students that responded to this. So it's a big data set. So that's lab 6. Why don't we go ahead and do that, and then I'll talk you through rotation. Oh, it's 1 o'clock. So much. Should I just talk through and then leave you to it? What do you reckon? Such strong feeling. Not all at once, please. I'm just going to talk you through it. That way, if people would like to leave, they're free to leave, right? If my voice can last. Okay, so rotation. This is the other thing to many people that differentiates a factor analysis from a PCA. Right? We know that a PCA, actually a factor analysis and a PCA, if you've got a lot of variables, are going to give very similar results in all likelihood, right? But the rotation of factors is something that is, you can do with a PCA if you want to actually, but it's pretty much unique in the literature to factor analysis. So, okay, you've done your factor analysis, right? Which is much like a PCA, right? You've chosen the number of factors that you want to extract, but what you can do then is rotate those factors to try and improve your meaning, interpretability, right? So what, that seems, when I first read that, I thought, well, hell, we can't do that. That's cheating. How can I then just choose, here's my eigenvector 1, 2, and 3. I'm just going to rotate them? Well, what am I doing with those eigenvectors? I don't know. That's what I was thinking, right? That was and then I realized, well, hell, the eigenvectors are just a basis that's describing the data cloud, right? Sure, that first eigenvector is chosen to maximize variation, but maybe that's not the good name of the game. Maybe I'm not trying to just find a map that describes the data as well as it can. Maybe I am interested in interpreting what that eigenvector is, right? So if I can rotate it in a way that will somehow ease my interpretation of it, that's a good thing. I will lose this ability, my ability to say, hey, look, these eigenvectors now I will basically end up with eigenvectors that won't necessarily be describing the most amount of variation, but if that wasn't my goal, who cares, right? So the fundamental idea of factor analysis is that it's actually invariant to rotations. You can get a whole bunch of solutions, which is going to provide the same correlation matrix, right? What we want to do is basically come up with a solution that we can interpret. Right? So let me give you an example. Here we have two factors, right? So think of this as like a PCA plot, if you like, or a biplot, essentially. Now these are the individual variables in my PCA plot or in my factor analysis plot. Right? So they are the variables: keeps me awake, works quickly, stops pain, no upset stomach, no side effects, limited relief. Right? So what is factor 1 describing? Well, it's a little bit of everything. If I rotate this around, right, I actually rotate the factor around so it's like that, then what have I got? I've got factor 1 talking about relief. I've got on this axis is basically talking about things stopping pain or working quickly as opposed to not working very well. And factor 2 is we can ascribe a simple meaning. It either keeps me awake or it doesn't have side effects. So this is factor 2 is a side effects factor basically, right? This is the underlying construct behind factor 2 now would be side effects. And factor 2 is how well it works, right? And this is because I've just rotated these results to ease my interpretation of it. Does that make sense? Right? Whereas before, factor 1, before I did the rotation, what's this thing? Factor 1, sure, it's a little bit about easing relief, and it's also a little bit about side effects, and likewise with factor 2, right? So we want to rotate it such that we have heavy loadings of certain variables only on certain factors and not on the other factors, right?
I have a question here. I mean, the rotation should be in the same percentage with respect for all variables. Right?
Yeah. So these would be all variables, right?
But it's not the case here. If you see, I mean, if you see they keep me awake, it's almost on the downside, and it's not just a rotation. It's something more than rotation.
Okay, I could have flipped it. Right, it's the other thing. Well, hey, let's see. Stops pain. You can flip these things, right? So you're right. I could have had keeps me awake here, but I can flip factor 1 so it's this way, and so keeps me awake is actually pointing in that direction, and everything else
Oh,
gets
yeah.
flipped as well, and then it would actually be a rotation then, right? Or splitting nice. No, it's not.
What I'm trying to say is that the rotation angle should be similar to all variables, not to selective variables.
Okay, so how's it doing? So essentially we're doing rotation on factor
It's rotated then, like,
factor relief. So we're saying there's a rotation of approximately 45 degrees here, right? Keeps you awake, but this one is actually being flipped. So really, if we think about this like this, so keeps you awake should be at the top, no side effects, stop, that should be at the bottom, right? So these things are the wrong way around. Yeah, but the meaning would be the same. I don't know why it's sort of like that, actually. Yeah, but the meaning, the interpretation would still be the same, and that keeps me awake. But the factor 2 is basically about side effects. And factor 1 is about, right? So how does it do this? Well, what it does, you don't actually choose the rotation. What you're trying to do is the computer gets to choose the rotation. It has a variety of ways of doing it, and it will choose it such that perhaps one of the most common ways is something called the Barry-Max rotation. So it's trying to choose or trying to rotate the data such that the variation amongst your of your factors, of the loadings of your factors is maximized, right? You're trying to basically make sure that the loadings, the distance that we've got along each factor is as big as we can get, right? It's called a Barry-Max rotation. So that's what we've got here. If you look at it, the total variation is going to be bigger across factor 1 and factor 2. Well, if you look at these columns, than they were originally. Right? So, and then things get a little bit funky here, because you don't actually have to rotate things such that they are orthogonal to one another, if you want to. And this is a little bit difficult to wrap your head around, in my view. Right? So, sure, we can do a rotation, but so that things are nice and orthogonal to one another. But if we think there is actually a relationship between the explanatory variables anyway, right? Why keep them orthogonal? Why keep them at right angles to one another? If we think consumer confidence and buying power are in fact not orthogonal, perhaps they should be allowed to rotate further, right? So it's an oblique rotation. So by far the most common rotational method is the Barry-Max orthogonal method. Right? So you're just trying to maximize the variance of the columns of your loadings, right? The oblique rotation basically does the Barry-Max rotation, and then it relaxes this orthogonality constraint and lets you move the axes a little bit more, so that they're not necessarily at right angles to one another, right? This can be a little bit dodgy, but you can see certain aspects where certain scenarios where it will be useful. Right, so let me show you an example. Say a researcher is creating a scale to measure 2 dimensions of customer satisfaction, brand loyalty, and perceived product reliability. These 2 constructs are likely to be associated. So in that instance, which type of rotation should you use? An orthogonal or ornithological, oblique, obligatory, I have no idea. Clearly ornithological, right? You guys know what ornithological means? Dealing with ornithology is the study of birds. So I think most of you would probably realize that, hey look, if your 2 constructs are in fact related to one another, right, then perhaps we should be using a set of axes that are not completely orthogonal to one another as well. Okay. So we end up with a rotated factor pattern matrix. It's the matrix of standardized regression coefficients for the rotated factors. It's equal to the correlations between the variables and the rotated factors, if you've got orthogonal rotations. Right? So most of this then is about SAS. Now I think that at the end, the displayed factor analysis, your factor loading plots. This is mainly going to be done in the lab. The final communality estimates are called squared canonical correlations, if we're going to use the maximum likelihood method, right? They basically are the amount of variation that's explained by each factor, right? And so that, is there any much more? That's about it, right? So let's just summarize, and then I'll be done with the block. Rotated factor patterns help you name the factors, basically, right? So we've done essentially what is very similar to a PCA, and we've got your eigenvectors through there, right? Or you might have done it through a maximum likelihood method, right? But then you're going to let it rotate further, potentially, to try and help try and maximize the variation of your loadings. So you've got lots of zeros and then some really big loadings. You're more likely to get that sort of scenario. And that hopefully you'll be able to interpret that, right? Because of the fact that you've got distinct loadings on for distinct variables on distinct factors, on specific factors, right? So you're going to, hopefully you'll be able to name your factors in some way. So you're going to look for items that are strongly associated with that factor. You're going to consider whether items that load on a factor reflect a common phenomenon, and this is going to be your underlying construct, right? So factor analysis, right? So I've talked about these underlying constructs as if you know them, but the reality is you just you do the analysis and then you try and see what's going on, right? Do these things actually, or do these big loadings actually relate to something that is interpretable? And we can use our squared canonical correlations to explain how much noise is left in the variables. Okay, this is good. Now we're going to talk about that. All right, so that's all I have to say about exploratory factor analysis. We go ahead and do the labs. Okay, and practical 5, you're welcome to do. Obviously, I would hope you can do practical 5 in the lab as well. If not, so practical 5, all of the practicals are due in 2 weeks, right? 2 weeks from now, 1:30. Are they better or worse? Mine is better. Okay, I will sell them more. I have more. I'll sell them for a limited price. Really, are they much different? I'll have a look. Okay.